The Biopod hatch seals with a pneumatic hiss, locking you inside a climate-controlled crystal dome. Overhead, full-spectrum LEDs bathe the hydroponic rows in a gentle violet glow. A synthesized voice, resonant and calm, speaks from every direction. Attention, candidate. You have entered the Water Wisdom Simulator. This is not an arbitrary puzzle. It is a test of your ability to steward Earth's most precious liquid. To exit, you must allocate a finite water supply between two crops to maximize total food output. Your oxygen reserves will last precisely 10 minutes. Should you fail, you will remain here as a permanent hydroponicist, tending algae forever. Your pulse quickens. The voice continues, enunciating each word with scientific precision. You have been granted exactly 50 liters of water. Not a single drop more, not a drop less. Before you stand two genetically improved crops, tomato, a vigorous indeterminate vine, and chili, a compact bush bearing pungent fruit. Their yields are governed by well-established water production functions. For tomato, y subscript t equals 15, open parenthesis, 1 minus the exponential function of negative 0.3 times w subscript t, close parenthesis, kilograms. For chili, y subscript c equals 8, open parenthesis, 1 minus the exponential function of negative 0.5 times w subscript c, close parenthesis, kilograms. Here, w subscript t is the water in liters delivered to tomato, and w subscript c the water to chili. The constraint is absolute. W subscript t plus w subscript c must equal 50 exactly. You may not store or waste any water. Your goal is to find the values of w subscript t and w subscript c, each rounded to 2 decimal places, that maximize the total harvest. Y subscript total equals y subscript t plus y subscript c. Input your answer when ready. A holographic timer materializes, displaying 10 minutes. The seconds start to decrement with a soft, rhythmic beep, each one amplifying the tension. You take in the scene. Beyond the dome, a vast, parched landscape stretches under a harsh sun, a window to a world where water mismanagement has turned fertile plains to dust. This simulation is not fiction. It mirrors the daily choices of millions of farmers. In the Indus Basin in California's Central Valley, across the Sahel, growers must decide how to share limited water among wheat, maize, vegetables. Over-irrigate and aquifers deplete, energy is wasted, soils salinize, under-irrigate and yields collapse, jeopardizing food security. The mathematical functions before you embody the law of diminishing returns. Each extra liter of water adds less and less harvest. The marginal yield, the derivative, tells you the additional kilograms from 1 more liter. For tomato, the marginal yield is 4.5 e to the negative 0.3 w subscript t. For chili, it is 4 e to the negative 0.5 w subscript c. At the optimal split, these marginal yields must be equal, because if one crop gave more per liter, you could shift a tiny amount of water and increase total food. The voice, sensing your thoughts, offers a clue. Remember, the derivative of e to the power of a constant times x is that constant times e to the power of a constant times x. Use calculus to balance the margins. The keypad will only accept one attempt. Time trickles away. Around you, the roots receive precise droplets through a network of thin tubes, a model of drip irrigation, which can save up to 60% of water compared to flood methods. Worldwide, agriculture consumes about 70% of freshwater withdrawals, and inefficient allocation wastes billions of liters daily. Solving this riddle is not just about escaping a dome. It is a mental exercise that mirrors the optimization algorithms used by agronomists and engineers to design water-smart farming systems. When you determine the optimal split, you symbolically help quench a thirsty planet. You recall the water footprint of common foods. A kilogram of tomatoes takes about 200 liters of virtual water. Chilies, even more. Every drop in this simulation represents thousands of liters in the real world. The equations may seem abstract, but they are the same kind used by the Food and Agriculture Organization to optimize crop patterns in water-scarce regions. The derivative you are about to equate is the marginal water productivity, a concept at the heart of sustainable irrigation. If you shift a milliliter from tomato to chili, the change in total yield is the difference of those marginal products. The optimal point is where that difference is 0. The voice, perhaps reading your thoughts, adds a softer hint. Set the derivative of total yield with respect to w subscript t to 0. You will get an equation that leads to an exponential term equal to a number. Then use the natural logarithm. The timer now shows 7 minutes. The beep seems to synchronize with your heartbeat. Outside, the virtual sun bakes the digital landscape, a reminder of the relentless evaporation that steals water from reservoirs worldwide, up to 3,000 billion liters annually from open canals in hot climates. Solving this puzzle correctly will not only open the door but also serve as a parable for efficient allocation, using less water to grow more food, a necessity as the global population nears 8 billion. The roots continue to receive their droplets, each one perfectly timed. The keypad glows brighter, as if impatient. The equation you will solve is transcendental, but tractable. Multiply both sides, isolate the exponential, take the natural log. The numbers will reveal themselves. Every second counts. The oxygen level is still safe, but the psychological pressure mounts. You recall that similar optimization problems are used in factory production, investment portfolios, and even in the distribution of medical supplies during a crisis. The principle of equating marginal contributions lies at the core of resource economics. Now the timer shows 6 minutes. The beep has become a metronome of your focus. The keypad blinks, a silent invitation. The fate of the dome and the symbolic future of water-wise farming rests on your input. You nod, steadying your fingers above the glowing digits. The world in microcosm waits. The seconds feel like hours. You have all the knowledge needed. Now the equation is ready. The voice returns, its tone imbued with a hint of encouragement. Candidate, the moment of decision is near. Enter W subscript T and W subscript C, each to 2 decimal places, to unlock the hatch and carry this lesson beyond these walls. What numbers will you input?